A 60-ton animal hangs motionless in total darkness, a mile below the surface. Its head takes up a third of its entire body. Inside that head sits an organ no scientist fully understands, and once a minute it fires a sound louder than a jet engine into the black water. We are going inside the sperm whale, the largest brain on Earth. A stomach filled with the beaks of monsters, a waxy treasure worth more than gold, and a sound that might stun or kill before the whale ever opens its mouth. If you enjoy what we cover, subscribe and leave a like. Prepare yourselves, we begin. There is an animal alive right now that has been diving to the bottom of the ocean since before humans existed. It was hunting in total darkness while our ancestors were still figuring out fire. And for most of human history, we had no idea what it actually was. The sperm whale, the largest toothed predator on Earth. A confirmed fact, not a guess. Picture a school bus. Now picture 9 of them lined up end to end. That is roughly the length of a full-grown male sperm whale. He weighs about as much as 10 elephants stacked together, and almost all of that weight is pure, specialized hunting machine. For centuries, sailors reported a creature with a massive square head and a jaw full of teeth rising from the sea and dragging ships down. Some of those stories grew into myths. The kraken, sea monsters, the kind of thing you carve onto the edges of old maps where the ocean runs out of names. But the animal was real, more terrifying than the myth, because the myth was something unknowable and magical. The sperm whale is something that actually exists right now in oceans you could drive to. Here is what we confirmed. Males grow up to 60 feet long. Females are smaller, closer to 40 feet. They breathe air, give birth to live calves, and produce warm milk. By every technical definition, they are mammals. Your distant cousins, adapted over millions of years to conquer a world that would kill you in minutes. The name comes from the waxy substance inside their heads, which early whalers mistook for reproductive fluid. They called it spermaceti. The name stuck even after scientists figured out what it actually was, or tried to figure out what it was. That story comes later. Sperm whales have existed in roughly their current form for around 23 million years. That means they survived every major extinction event in the last 23 million years of Earth's history. Whatever killed the giant reptiles, whatever froze the continents, whatever shifted the ocean currents and starved entire ecosystems, the sperm whale kept going. It adapted. It dove deeper, hunted harder, and kept moving. By the time humans started sailing the open ocean, the sperm whale had already been running the deep sea for longer than our entire species has existed. When the whaling industry peaked in the 1800s, hunters chased them across every ocean on Earth. Sperm whales were the prize above all prizes. Their heads contained oil that burned cleaner than anything else available. Their intestines sometimes held a substance worth a fortune. Ships crossed 10,000 miles of ocean for a single whale. And even then, at the height of the hunt, the whalers admitted they were dealing with something that fought back in ways they did not expect. There are confirmed accounts of male sperm whales ramming wooden ships at full speed, deliberately. The most famous case sank a vessel called the Essex in the middle of the Pacific Ocean in 1820. The crew spent months adrift. Most of them died. The whale did that on purpose. Scientists believe it. The behavior fits patterns seen in other large, intelligent animals defending their pods. So before we go inside this animal, understand what we are looking at: an apex predator with 23 million years of evolution behind it, a brain bigger than any creature on Earth, a body built for pressures that would crush steel, and a head full of something that still confuses the best marine biologists alive today. That square head is where everything starts, and what is living inside it will change how you see this animal forever. The first time a scientist dissected a sperm whale head, they expected something like every other whale they had studied: bone, muscle, fat, standard anatomy. What they found stopped them cold. The square head of a sperm whale is one of the strangest structures in the entire animal kingdom. From the outside, it looks almost geometric, flat in the front, massive, like someone welded a rectangular box onto the front of an enormous torpedo body. It accounts for more than a third of the animal's total length and a third of its total body weight. Inside, the anatomy gets stranger fast. The skull itself sits far back in the head, closer to the middle of the body than the front. The face you see when a sperm whale surfaces is almost entirely soft tissue, enormous, organized, purposeful soft tissue, tubes, sacs, chambers, canals filled with oil that has a completely different composition from regular whale blubber. Marine biologists call the whole structure the melon complex, but that word does not capture what it actually is. This is a biological machine, a system of interconnected parts that work together to do something scientists have been arguing about for over 100 years. The front section of the head contains the spermaceti organ, a massive sac running the length of the snout, filled with a waxy liquid oil. In a large adult male, this organ alone can hold around 500 gallons of the substance. Picture a hot tub, then fill it with dense yellowish wax that is sitting inside the whale's face right now. Behind and below the spermaceti organ sits a second structure called the junk. Despite the casual name, it is anything but. The junk is a series of separated compartments, each one also filled with spermaceti oil, separated by thin layers of connective tissue. It looks like a honeycomb made of wax and flesh. Together, the spermaceti organ and the junk take up most of the interior of the head. There is almost no room for anything else in the front third of this animal's body except these two structures and the tubes that connect them. Here is what baffles scientists. Nothing else in nature does this. No other animal on land or in the sea has a head built like this. The closest comparison would be the sonar dome on a submarine, but the whale grew this structure naturally, over millions of years, without any engineer drawing up plans. What is it for? Scientists have 3 serious theories. We will go through each one in the coming chapters because each one reveals something different and disturbing about this animal. For now, understand the basic puzzle. A structure this large, this complex, this metabolically expensive to maintain, has to do something critical. Animals do not carry around organs that weigh thousands of pounds for no reason. The sperm whale evolved this head because it needed it, desperately, in the darkest, most hostile place on Earth. And whatever this head does, it does it better than any technology humans have built for the same purpose. One of those purposes involves sound, specifically sound that scientists describe as the loudest biological noise ever recorded on Earth. You are about to hear what that means. Give researchers enough time, enough equipment, enough dead whales to examine, and eventually the answer comes together. The spermaceti organ has resisted every attempt to fully explain it for over 2 centuries. Confirmed fact, it exists. Confirmed fact, it is enormous. Everything else is still being argued. Here is what we know for certain. The organ sits inside the upper portion of the whale's square head, running from just behind the blowhole almost to the tip of the snout. In a large adult male, it stretches roughly 14 feet long, that is longer than most cars. It is wrapped in a thick muscular sheath, like a casing, and connected by a series of tubes to the structures around it. The oil inside it is called spermaceti. At body temperature, it is liquid. When the temperature drops, it thickens into a waxy solid. This transition from liquid to solid and back again is central to every major theory about what the organ actually does. Whalers in the 1800s treated it as a resource. They drilled holes into the heads of dead whales and ladled out the oil by the bucket. A single large male could yield over 500 gallons. They used it for candles, for lubricating machinery, for lamp fuel. It burned cleanly and did not smell. Industry loved it. But what did the whale use it for? Theory 1. Acoustic amplification. The spermaceti organ acts as a giant reverb chamber for sound. The whale generates a click at a structure near the front of its skull, and that click bounces back and forth through the oil, amplifying it to enormous volume before the wave exits through the front of the head. Think of cupping your hands around your mouth, but instead of hands, you have 14 feet of dense wax, amplifying every vibration. This theory has the most scientific support. Theory 2. Buoyancy control. Some researchers believe the whale can deliberately change the temperature of the oil by drawing cold seawater through connecting tubes. As the oil cools, it becomes denser. As it warms, it becomes lighter. This might allow the whale to fine-tune its weight during a dive, sinking faster or rising more slowly without burning extra energy. Like adjusting the ballast tanks on a submarine, but biological and self-regulating. Theory 3. A battering ram. The spermaceti organ in a large male is a dense padded mass sitting in the front of the skull. Some scientists believe male sperm whales use their heads as weapons in competition with other males, ramming each other at depth. The structure of the organ, with its oil-separated compartments, could absorb the impact of a head-on collision without damaging the brain behind it. The Essex incident fits this theory too. None of these theories cancel each other out. The organ might do all three things. And that possibility is exactly what makes it so unsettling. A single biological structure that navigates in darkness, controls depth without engines, and doubles as a weapon is beyond anything human engineers have packed into the same space. And none of that explains what the whale does with the sound once it leaves the head. That is where things move, from strange to almost unbelievable. Close your eyes and imagine standing on an airport runway as a jumbo jet passes overhead at full throttle. That sound hits you at around 140 decibels. It rattles your chest. It makes your teeth ache. Exposure for more than a few seconds starts damaging your hearing permanently. A sperm whale produces clicks that reach around 230 decibels. Underwater, confirmed by researchers using hydrophones, which are underwater microphones. That is not a small difference. The decibel scale works exponentially, meaning each 10-unit jump represents roughly 10 times the sound intensity. The jump from 140 to 230 is enormous. The whale's click is physically more intense than the jet engine, by an enormous margin. Now here is the part that takes a moment to process. The whale makes this sound with no vocal cords, no larynx, no air being pushed through a tightened opening the way humans produce voice. The sound comes from a small, dense structure inside the skull called the museau du singe, which translates from French to monkey's muzzle. Researchers named it that because of the way it looks during dissection. The monkey's muzzle sits just inside the whale's right nostril passage, near the front of the head. When the whale forces air through it at high pressure, it vibrates and produces a click. That click travels backward through the spermaceti organ, bounces off a reflective structure at the back of the skull called the frontal sac, then travels forward again, through the junk, and out through the front of the whale's head. The oil in the spermaceti organ focuses the sound the way a lens focuses light. It shapes the beam, compresses it, and sends it forward in a directed pulse rather than just a random burst of noise scattered in all directions. The result is a click so precise and so powerful that it functions as a biological sonar system. The sound travels out into the dark water, hits an object, and bounces back. The whale reads the returning echo and builds a detailed picture of its surroundings without using its eyes at all. In water completely dark to human eyes, the whale sees the shape of the seafloor, the outline of prey, and the position of other whales, all through sound alone. Scientists call this echolocation. Bats use a version of it in air. Dolphins use a softer version in shallow water. The sperm whale uses the most powerful version of it that exists in any living creature on Earth. Each click lasts a fraction of a second. The whale fires them in rapid sequences called codas, patterns of clicks that carry information scientists are still working to decode. The pattern varies by region. Whales in the Pacific click differently from whales in the Atlantic. Those differences are consistent within groups and passed between generations. The whale essentially speaks in a dialect, but the sound does more than map the dark. Some of those clicks travel at a power level that the ocean itself cannot fully absorb before they reach their target. And what happens when a beam of sound that powerful hits a living creature up close is something scientists still debate fiercely. Picture a giant squid. It lives at a depth of around 3,000 feet, in total darkness, and it can grow to the length of a school bus. It has 8 arms, 2 feeding tentacles lined with razor-edged suckers, and eyes the size of basketballs. It is one of the fastest, most agile creatures in the ocean at that depth. The sperm whale eats them regularly, in enormous numbers. Here is the problem. A sperm whale is enormous, and enormous things are slow to turn. A giant squid, by comparison, is built for speed and evasion. The whale should have serious difficulty catching it, especially in pitch-black water where both animals are hunting by feel and sound. And yet, scientists have found no clear evidence of a long physical chase in sperm whale stomachs. The squid beaks they recover are largely intact. The tentacles show little sign of the frantic, thrashing struggle you would expect from a prey animal fighting for its life. Some marine biologists believe the whale never chases the squid at all. They believe it stuns it first. This is a theory, not a confirmed fact. But the evidence behind it is serious. The clicks a sperm whale fires during a hunt, called creak clicks by researchers because of the rapid creaking sound they produce, come at a dramatically higher rate than normal navigation clicks. The whale accelerates its click rate as it closes in on prey, the same way a bat increases its echolocation pulses just before catching an insect. At close range, that rapid-fire burst of sound at 230 decibels would hit a squid with an enormous wave of acoustic energy. Scientists know that intense sound waves can physically disrupt tissue. Underwater, sound waves compress and expand the water around them. A sufficiently powerful wave, at the right frequency and close enough range, can cause pressure damage inside a living body. Laboratory tests on fish exposed to high-intensity underwater sound have shown temporary paralysis, loss of coordination, and in some cases, tissue rupture. Squids, with their soft bodies and no hard internal skeleton to absorb impact, may be especially vulnerable. Some researchers have pointed to videos of sperm whales hunting in slow, almost casual sweeps, never appearing to rush, and argued that the prey is already incapacitated by the time the whale arrives. The whale opens its narrow jaw and simply collects what the sound already defeated. A few scientists go further. They suggest the whale can aim and modulate the beam, focusing the click into a tighter pulse for short-range stunning and spreading it wider for long-range navigation. A biological weapon with a range setting. This has never been directly observed or measured in the wild. The depths where sperm whales hunt are nearly unreachable by human equipment. We cannot send a camera to 3,000 feet and follow a whale through a hunt in real time. The ocean keeps that secret. What we do know is this: the whale almost always wins. An animal built for speed and evasion, operating on home territory in total darkness, keeps ending up in the stomach of a creature that descended from above. Something is giving the whale an edge we have not fully explained yet. And when the hunt ends, the whale rises back toward the surface. That journey takes time, and what happens to the whale's body on the way up raises an entirely different set of impossible questions. A sperm whale click lasts less than 1 millisecond. That is 1,000th of a second. That silence is the important part. When the click leaves the whale's head, it travels outward through the water at around 1 mile per second. Sound moves faster underwater than it does in air, which is part of why it retains so much energy over distance. The click travels until it hits something: a rock formation, a school of fish, the sloping seafloor, the rising wall of an underwater canyon. Then it bounces back. The whale listens during the silence. The returning echo arrives at the whale's lower jaw, which is filled with a thin layer of oil that runs directly to the inner ear. That jaw acts as an acoustic antenna, picking up the returning sound and feeding it into the whale's auditory system. The whale's brain processes the time gap between the outgoing click and the returning echo, and from that gap alone calculates the exact distance to the object that reflected it. This is the same basic math your phone uses when a GPS signal bounces off a satellite. The whale figured it out 60 million years before the satellite was invented. But the system is more refined than simple distance calculation. The whale also reads the shape of the returning echo. A hard, flat rock returns a different echo than a soft, rounded fish. A school of small squid returns a different pattern than a single large one. The whale can identify what it is listening to without seeing it at all. Scientists discovered something fascinating about how the whale times its clicks. The gap between each click is almost exactly equal to the travel time of the echo. When the whale is hunting something far away, the clicks are more spread out. As it closes in, the clicks get faster. The whale is essentially syncing its click rate to the round-trip travel time of its own sound beam, so it is always listening during the silence and never firing a new click while an echo is still returning. This is precision engineering, built into the brain and body of a living animal. The range of the system is staggering. Research vessels using hydrophones have detected sperm whale clicks from over a mile away through open water. Within that range, the whale can build a three-dimensional acoustic map of everything around it in complete darkness at 3,000 feet of depth. No human sonar system achieves the same combination of range, resolution, and energy efficiency in a package this size. Navies around the world have studied the sperm whale's sonar for decades. The United States Navy has funded research into biological sonar systems specifically because the whale does something artificial systems have not been able to replicate. It produces an enormously powerful signal and receives an enormously detailed echo using the same organ without the outgoing blast overwhelming the incoming return. The whale solved a noise suppression problem that human engineers still work on. And all of this sound, all of this biological technology, is running through a brain that makes the human brain look small by comparison. That brain is the next stop, and its size alone is only the beginning of why it matters. Pull a human brain out of the skull, and it weighs about 3 pounds. That is the 3-pound organ responsible for every thought you have ever had, every memory you carry, every emotion you feel. 3 pounds of tissue that reads, dreams, grieves, invents, and loves. A sperm whale brain weighs about 18 pounds. Confirmed. It is the largest brain of any animal on Earth by weight, and the structure of that brain tells scientists something that goes beyond simple size comparisons. The outer layer of the brain, the part called the cortex, is where complex thinking happens in mammals. In humans, it is dense and folded, packed with billions of neurons. In sperm whales, the cortex is also dense, also folded and massively expanded in specific regions. One of those regions is associated with social communication. Another is linked to self-awareness. In humans, damage to the self-awareness region produces conditions where a person can no longer recognize themselves in a mirror, no longer plan for the future, no longer understand their own emotions. Sperm whales have an equivalent region expanded even further than in humans, relative to the size of the surrounding brain structures. Scientists use careful language here. They say the evidence suggests high cognitive complexity, meaning the brain is built for more than basic survival. They do not yet claim sperm whales are conscious in the way humans are conscious, but the biology points towards something more complex than anyone expected from an ocean animal. The sperm whale also has spindle neurons. These are long, slender brain cells that appear in humans, great apes, elephants, and a handful of other species considered highly intelligent. They allow fast, long-range communication between distant regions of the brain. They are associated with rapid social decision-making, reading the emotions of others, and feeling empathy. Sperm whales have spindle neurons in large numbers. This is a confirmed anatomical fact. The implication is uncomfortable for some researchers. An animal with this brain structure, with this level of social organization, may be experiencing something recognizable as emotion, attachment to family members, grief at loss, recognition of self. The whale's brain is also adapted in ways that have no human equivalent. The auditory processing regions are dramatically enlarged, which makes sense for an animal that hunts and communicates entirely through sound. The regions that process echolocation data are expanded to a degree that has no comparison in any land animal. The whale essentially devotes enormous neural resources to building acoustic pictures of the world. Its reality is probably sound in the same way our reality is built on vision. The whale thinks in echoes, and it uses that brain in ways that go far beyond hunting. Social structures in sperm whale pods reveal behaviors that shocked researchers when they first catalogued them. The size of the brain only raised the first question. What the whale does with it in its daily life inside the pod answered that question, in a way nobody was fully prepared for. Marine biologists following sperm whale pods in the Atlantic made an observation that stopped their research team's conversations cold. A female whale died. The other females in the pod stayed with the body for days. They circled it. They touched it repeatedly with their jaws. They kept returning even after the carcass began to sink. This behavior has been documented multiple times across different oceans. Confirmed. Sperm whales form matrilineal pods, meaning family groups led by and built around related females. Adult males spend much of their adult lives alone or in loose male groups, visiting female pods to mate. But the core of sperm whale society is a group of mothers, daughters, aunts and grandmothers who travel together for their entire lives. Within those pods, females cooperate in raising calves, in a way that researchers compare to elephant herds and some primate societies. A nursing calf does not feed exclusively from its own mother. Other females in the pod babysit. When a mother dives deep to hunt, something she must do to feed herself, she cannot bring a young calf down with her. The pressure and darkness would be lethal for the newborn. So the calf waits near the surface, and other females stay up with it, keeping it safe and sometimes even nursing it themselves. Scientists call this alloparenting. It requires the whale to recognize the calf as a member of the group worth protecting, even though it is not her own offspring. It requires long-term social memory, the ability to track relationships across time and know who belongs to whom. The memory required for this runs deep. Sperm whales live for around 70 years. Confirmed. Over a lifetime, an individual female interacts with dozens of other whales in her pod. She remembers social histories, alliances, and probably individual identities across decades. There is evidence that older females hold critical knowledge. Pods with elderly females navigate better, find food more reliably, and raise more calves successfully. Remove the oldest female, and the pod's performance drops measurably. The grandmother effect, well documented in elephants and humans, appears to operate in sperm whale society too. None of this was expected from an ocean animal. Researchers who study fish do not find grief, they do not find cooperative childcare, they do not find behavior that looks like mourning a dead family member. The sperm whale does all of it, and the more researchers study the pod's internal behaviors, the more a disturbing question grows. If this animal forms lasting bonds, recognizes individual family members, and appears to mourn the dead, what does the history of human whaling look like from inside the pod? Whaling ships did not take individual whales in isolation. They took mothers. They took calves. Entire family lines were eliminated in single hunts. The whales that survived watched that happen, with the largest brain on Earth and a memory that runs for decades. That history is still in the ocean, and the pods still exist. But before we go further into what the whale feels, we need to understand how it physically sustains itself, starting with one of the strangest digestive systems ever discovered in any animal. Fueling a 60-ton body is a serious engineering problem. The sperm whale solves it by eating enormous amounts of food and running it through one of the most complex digestive systems in the ocean. Confirmed. Sperm whales have 4 separate stomachs. Each one serves a different function. Together, they form a processing chain designed to break down prey that would defeat the digestive system of almost any other animal on Earth. Stomach 1 is the holding chamber. Food arrives here first, and the stomach's muscular walls begin physically grinding it down. The sperm whale does not chew the way land animals do. Its narrow lower jaw with its rows of conical teeth grabs prey, but the teeth are not used for chewing, they are for gripping. The real breakdown starts in the first stomach, where powerful muscle contractions crush the food against itself. Stomach 2 handles the chemical breakdown. Acids and enzymes here are concentrated enough to dissolve the tough muscle tissue of giant squid. These are animals whose flesh resists most predators precisely because it is so dense. The sperm whale's second stomach produces digestive chemicals strong enough to handle it. Stomach 3 absorbs nutrients and filters the dissolved material, separating what the body can use from what it cannot. Stomach 4 is where indigestible material accumulates. Squid beaks, the hard biting structures at the center of the squid's body, survive the first 3 stomachs because they are made of a material called chitin, which resists acid. In most cases, the whale vomits them back out before they reach this stage, but some beaks slip through. And what happens to those beaks in the 4th stomach is one of the strangest biological stories in the ocean. A healthy adult sperm whale eats close to a ton of food per day. Confirmed. That means the whale dives to extreme depths, stuns or captures prey, hauls it back up, and processes it through 4 stages of digestion, day after day, for a lifetime that stretches towards 70 years. The caloric demand of operating a 60-ton warm-blooded body in cold ocean water is enormous. The whale burns energy just maintaining its body temperature. It burns more energy in every dive. The hunting system has to be efficient enough to cover those costs and still leave surplus energy for growth, reproduction. Scientists calculate that a large male needs to catch several hundred pounds of squid per dive to break even. Several hundred pounds per dive in pitch-black water miles below the surface. The 4-stomach system is the downstream end of a hunting operation built around the whale's acoustic weapons, diving physiology, and intelligence. One feeds into the next. Every biological system in this animal is connected to every other system, and they all point toward a single purpose: keeping this enormous, warm-blooded predator alive at depths that nothing else its size can reach. But the stomach holds more than fuel. Some of what accumulates in that 4th chamber is not food at all. It is something stranger, something that has been washing up on beaches for thousands of years and confusing everyone who finds it. Here is something that sounds wrong at first. The largest toothed predator on Earth has teeth that scientists do not fully understand. And the upper jaw teeth are so underdeveloped they rarely break through the gum surface at all. Look at a sperm whale's skull, and the lower jaw is immediately striking. Between 36 and 50 large, conical teeth line the narrow lower jaw in 2 rows. Each tooth is dense ivory, roughly the shape and size of a human fist, and they fit into matching sockets in the upper jaw when the mouth closes. Confirmed anatomy. But flip that skull over and examine the upper jaw from the inside. The teeth are there, embedded in the bone, but most of them remain buried. Some never erupt at all. They stay trapped beneath the gum tissue for the animal's entire life. In older males, a few sometimes push through partially, but even then they are largely functionless. Why does the animal have upper jaw teeth at all if they serve no purpose? Evolution does not typically maintain expensive tissue without a reason. Growing teeth, even vestigial ones, requires resources: calcium, energy, cellular maintenance. An animal that carries useless teeth for 70 years is spending something on them. Scientists believe the upper teeth are a vestige of an earlier ancestor. Millions of years ago, the sperm whale's predecessors likely used both upper and lower teeth for active prey capture. As the whale's hunting strategy shifted toward the deep ocean and sonar-assisted hunting, the physical grip of the teeth became less critical. The lower teeth were enough. The upper teeth slowly became redundant, but evolution has not yet eliminated them completely. This is a snapshot of evolution in progress. The upper teeth are disappearing, generation by generation, over a timescale longer than human civilization. The lower teeth tell a different story. They are clearly functional, but researchers debate exactly how. During hunts, the whale's lower jaw hangs open as it approaches prey. The teeth are exposed. If the stunned squid theory holds, the teeth are mostly for the final collection of incapacitated prey. If the whale does physically wrestle large squid, the teeth provide grip during the struggle. In male-to-male conflict, the teeth appear more directly important. Males fighting for dominance show scarring patterns that match teeth marks from other sperm whales. The bites are deliberate, targeted, and apparently painful enough to leave permanent marks on animals whose skin is several inches thick. One consistent observation: female sperm whales raised in captivity have shown almost no interest in using their teeth for aggression. Males in the same settings use them routinely in dominance displays. The teeth may function differently depending on sex and age, which would explain why evolution maintained them in both upper and lower jaws, despite apparent redundancy in the upper set. A jaw this complex, with this history, tells a long story about where this animal came from and where it is heading. But what sits inside the jaw, deep in the digestive system at the end of the chain, holds a mystery that has baffled scientists, treasure hunters, and perfume makers for centuries. And it starts with those indigestible squid beaks that the whale cannot pass and cannot dissolve. The team approach the carcass carefully. A sperm whale dead on a beach draws researchers the way a crime scene draws detectives. Every stomach opened is a record of what lived in the deep ocean, a place human eyes almost never see. When the first stomach chamber finally opened, the smell hit them before anything else. Inside, mixed with partially digested tissue and dark fluid, were hundreds of squid beaks, all sizes, some as small as a fingernail, belonging to smaller squid species, others wider than a human palm, from animals that would have stretched longer than a car. Hundreds of beaks from a single whale's recent meals. This is what a sperm whale's stomach looks like after a few days of hunting, confirmed by numerous whale necropsies conducted by marine biologists around the world. The beaks are remarkable artifacts. Chitin, the material they are made from, resists decomposition. It survives acid that dissolves muscle and skin. Researchers can identify the squid species from a beak's shape, the same way a forensic expert identifies a victim from dental records. A single stomach becomes a species catalogue of what lived at that depth, in that part of the ocean, at that point in time. Scientists have used whale stomach contents to confirm the existence of squid species they had never observed alive. The whale's stomach provided the first physical evidence that certain deep-sea squid species existed at all, because the animals themselves lived too deep for nets or cameras to reach reliably. The whale was catching them for millions of years before we knew they were there. Giant squid beaks appear regularly. The giant squid, which can reach around 45 feet in length and weigh close to a ton, was considered a legend by most scientists until the late 20th century. Proof came partly from sperm whale stomachs. The beaks were there, the whale had been eating them all along. The size distribution of beaks in a single stomach tells researchers about hunting strategy. Multiple small beaks suggest the whale targeted a school of common squid in open water. A few very large beaks suggest the whale dove to extreme depth to engage a specific large prey animal. The stomach is a hunt diary. Sperm whale stomach contents have also revealed the remains of objects humans lost in the ocean. Ropes, pieces of netting, plastic bags mistaken for squid in dark water, One whale examined off the coast of Europe carried a collection of fishing line and packaging material in its digestive system that would fill a grocery bag. The beaks accumulate. Most get passed through eventually. But some slip into the fourth stomach and begin a process that takes years, possibly decades, producing a substance that washes ashore smelling like the inside of a garbage can, but sells for more per pound than gold. That substance and why it forms is the next part of this story, and the theory about how the whale gets rid of it involves something so disturbing that scientists still disagree about whether it is even survivable. Every sperm whale carries a record of its life on its skin. Run your eyes along the side of a large adult male and you find layers of damage, long parallel scratches from the teeth of other males. Round, perfectly circular depressions the size of dinner plates scattered across the head, the flanks, the sides of the jaw. Some healed completely, leaving pale scar tissue. Others still visible as raised ridges years after the injury. Those circular scars are the ones that matter most. They match, almost perfectly, the dimensions of the suckers on giant squid tentacles. Confirmed. Not the regular suckers from small squid. The scars on large adult males sometimes exceed 12 inches in diameter, matching the sucker rings of giant squid in the same size range as the largest ever measured. The whale and the squid fought in complete darkness at depths exceeding a mile, and both animals left marks on each other. This was not a clean hunt. The evidence rules that out. The scarring on some individuals covers most of the head and upper body. Some scars show the distinctive serrated edges of the toothed sucker rings that large squid species use to grip prey. The squid was trying to hold on, trying to pull the whale's head towards its beak, trying to do what giant squid do when they catch something. The whale won those encounters. It always won, because it is still alive and carrying the scars. But the fights were real, and they were violent. In male-on-male conflict, the bite marks from other sperm whales are even more dramatic. Males competing for access to females engage in combat that leaves gouge marks through skin several inches thick. The teeth of a large male, each one the size and density of a billiard ball, driven by jaw muscles capable of generating enormous force, produce injuries that would be life-threatening in most animals. Sperm whales survive because their skin and the blubber beneath it provide a layer of protection that few other animals possess. The outer skin of a large male can exceed 14 inches of combined skin and blubber, dense enough to absorb impacts that would penetrate most materials, but the scars accumulate over decades. A 60-year-old male is covered in a biography written in old injuries. Researchers reading those scars can estimate roughly how many major conflicts the animal survived, how large the squid it hunted were in different life stages, and sometimes even identify individuals across years of observation by their unique scar patterns. Each whale carries a different map. No two are identical. The scarring pattern is as distinctive as a fingerprint. What those scars cannot show directly is what the whale endures during the dive itself. The pressure at the depths where the largest squid live would kill a human being in seconds without any protective equipment. The whale descends into that environment, survives it, hunts in it, fights in it, and ascends back to breathable air. How the whale's body handles that pressure is the next impossible question. And the answer reveals an anatomy that should not work, but somehow always does. Descend 200 feet underwater in a pressurized dive suit, and you begin to feel the weight of the ocean. The pressure at that depth equals several atmospheres pressing against every square inch of your body. Human lungs, filled with air at the surface, compress toward your chest. Without a suit designed to counter that, the squeeze becomes dangerous fast. A sperm whale dives to depths exceeding 7,000 feet. The pressure at that depth is more than 200 times the atmospheric pressure at the surface. That is enough force to crush the hull of a standard submarine, which is typically designed for depths of around 1,000 feet. The whale does this without a suit, without machinery, without any external support. And then it comes back up and does it again. The first question most people ask, what happens to the lungs? The answer is counterintuitive. The whale does not fill its lungs with a massive breath before diving the way a human would. It takes a moderate breath, nowhere near a full lung capacity. Then, as the whale descends and pressure increases, the lungs compress. They do not fight the pressure. They yield to it. The air inside gets pushed out of the lungs and into the rigid upper airways, which do not compress, where it sits harmlessly until the whale ascends and the lungs expand again. By the time the whale reaches extreme depth, its lungs have collapsed almost completely. Confirmed, the chest cavity is built to allow this. Cartilage rings reinforce the airways while the lung tissue itself folds and flattens under the load. A human's lungs would tear during a forced collapse like this. The sperm whale's lungs are built for it. The tissue is flexible in specific ways, the blood supply is arranged to prevent hemorrhage during compression, and the surrounding structures provide a framework that keeps the collapsed lung from being injured. The rib cage also helps. Several of the whale's ribs connect to the spine but not to the sternum, making the chest cage partially flexible. The whole front of the body can squeeze inward slightly during a deep dive, accommodating the collapsed lungs and compressed organs without causing structural damage. While the lungs collapse, the whale's circulatory system redirects blood away from non-essential areas and concentrates it around the heart, brain, and the organs that must keep working under pressure. This is a diving reflex, similar to what happens in humans during brief submersion, but extended and amplified to a degree that has no human equivalent. The whole system works together as a single coordinated pressure response. No one organ handles the pressure alone. The lungs, ribs, circulatory system, and tissue composition all adapt simultaneously during every dive. The whale has done this every day of its life. Thousands of dives, millions of minutes at crashing depth. Surviving the pressure is one problem, but coming back up too fast creates a different danger, one that kills human divers with regularity and should logically threaten the whale too. That danger is still only partially understood in this animal, and the biological solution the whale uses has no simple explanation. For a long time, the lung collapse seemed like a dangerous side effect of diving deep, something the whale simply endured because the alternative was staying shallow. Researchers thought of it the way you might think of a bruise from heavy exercise. Painful, but unavoidable. Then the data started pointing in a different direction. Confirmed through research on multiple species of deep-diving whales and seals, the lung collapse is deliberate. It is a feature built into the whale's anatomy on purpose. Here is why that matters. When a human diver breathes compressed air at depth, the increased pressure forces nitrogen to dissolve into the bloodstream at much higher concentrations than normal. As long as the diver stays at depth, the nitrogen stays dissolved, but ascend too fast, and the pressure drops before the nitrogen can leave the body through the lungs. Instead, it bubbles out of the blood inside the body, forming gas bubbles in the joints, organs, and nervous system. This is decompression sickness, commonly called the bends. It causes crushing joint pain, strokes, paralysis, and death. Divers who ascend too fast die from their own blood turning to foam. The sperm whale ascends fast, very fast. After a hunt at extreme depth, the whale wants to get back to the surface quickly. A slow ascent would be metabolically expensive and potentially dangerous in different ways. The whale moves up at a speed that would kill a scuba diver without question. But the whale does not get the bends, confirmed by physiological studies. The reason is the lung collapse, because the lungs fold down and the air inside them gets pushed into the rigid, non-absorptive upper airways before the whale reaches depth. Very little of the pressurized air contacts the lung tissue, where gas exchange into the blood normally occurs. Less air in the lungs means less nitrogen being pushed into the bloodstream. By the time the whale reaches maximum depth, almost no nitrogen exchange is happening at all. The blood is not being loaded with dissolved gas the way a diver's blood is. When the whale ascends, there is almost no excess nitrogen to bubble out. The bends cannot develop because the conditions that cause the bends were never allowed to form. The whale essentially switches off gas exchange at depth by collapsing the exchange surface on purpose. It becomes temporarily a closed system for nitrogen. The oxygen it needs for that dive was already bound to proteins in the blood and muscle tissue before the dive began, stored in a form that does not require lung exchange to maintain. Those oxygen-storing proteins in the muscle are part of the next layer of this anatomy. They are why a sperm whale's muscle, when exposed to air during a necropsy, turns almost black. And they are the reason the whale can stay submerged for close to 90 minutes on a single breath. That 90-minute breath hold is confirmed. It is one of the longest confirmed dive durations of any mammal. And what the whale does during those 90 minutes at depth involves a mystery that nobody has solved cleanly. The lung collapse handles most of the nitrogen problem. But marine biologists discovered, after decades of study, that the collapse alone does not explain everything. Some nitrogen still gets into the bloodstream, small amounts during the descent phase before the lungs fully compress. Trace amounts from residual gas in the airways. The mathematics suggest that even these small amounts, accumulated over thousands of dives across a lifetime, should eventually cause problems. Chronic nitrogen buildup, damage to joints and bones similar to what long-term professional divers develop after years of repeated exposures. When scientists examined the bones of stranded sperm whales for signs of this damage, they found something unexpected. Some whales showed what looked like healed lesions on their bones, patterns consistent with past decompression events. A small number of whales appeared to carry old bone damage that looked to a bone pathologist like the kind of injury a human diver gets after a serious case of the bends. This was a troubling discovery. If the whales were experiencing low-level decompression events repeatedly throughout their lives, the lung collapse theory was only part of the story. Something else was compensating. One serious hypothesis involves the spleen. The spleen in marine mammals, including sperm whales, is dramatically enlarged compared to land animals. In a diving mammal, the spleen acts as a biological oxygen tank. It stores red blood cells packed with oxygen-carrying proteins. Just before a dive, the spleen contracts and releases a surge of oxygen-rich blood into circulation, giving the whale a last-second boost of available oxygen before descent. Some researchers believe the spleen also plays a role in nitrogen management. By controlling blood flow to specific regions of the body during a dive, the whale may reduce the surface area where nitrogen can dissolve into tissue, essentially rationing which parts of the body are exposed to whatever residual pressurized gas remains. A second hypothesis involves proteins in the blood itself. Sperm whale blood has a different composition from human blood. The hemoglobin molecules, which carry oxygen, have a different binding affinity that makes them more efficient at holding oxygen at low partial pressures. This means the whale needs less dissolved oxygen to sustain brain and heart function at depth than a human would, and the gas dynamics of the whole dive are therefore different. The honest scientific position right now is that the whale manages nitrogen through at least 3 separate overlapping systems: the lung collapse that minimizes uptake, the blood protein adaptation that reduces demand, and possibly the spleen and circulatory shunting that limits distribution. Together, they solve the problem. Alone, none of them is a complete answer. The whale figured out the bends tens of millions of years before we knew what the bends were, and somewhere in the middle of all this diving physiology, a second major mystery lives inside the head. A mystery that connects the sound the whale makes to the depth it reaches, in a way that requires the spermaceti organ to do something no organ in any other animal does. A large male sperm whale weighs around 60 tons. Getting something that heavy to sink rapidly to a depth of several thousand feet and then return to the surface efficiently requires an enormous amount of energy. Or it requires a system that reduces the energy cost of the descent and ascent dramatically. This is where the spermaceti organ enters from a completely different angle. The buoyancy theory goes like this. The spermaceti oil inside the organ exists at two different densities, depending on its temperature. When the oil is warm, at the whale's internal body temperature of around 95 degrees Fahrenheit, it is liquid and relatively light. When the oil cools, it thickens toward a waxy solid and becomes denser. A denser spermaceti organ makes the whale's head heavier. A heavier head, especially one accounting for a third of the body's total weight, shifts the animal's overall buoyancy toward negative. The whale sinks more easily because its front end is heavier. A lighter, warmer organ shifts buoyancy toward neutral or positive. The whale rises more easily. If the whale can actively control the temperature of the organ during a dive, it could manage its buoyancy throughout the descent and ascent without burning massive amounts of muscle energy to stay at depth or rise to the surface. The proposed mechanism involves the whale's circulation. During descent, the whale could restrict blood flow to the spermaceti organ, allowing the oil to cool as the surrounding seawater draws heat away. As the oil cools and solidifies, the head gets heavier and the whale sinks with less effort. At the bottom, the whale could increase blood circulation to the organ, warming the oil back toward liquid and reducing the density, helping the ascent. This theory is plausible and fits the known biology. The spermaceti organ does have a rich blood supply. The oil does change density with temperature. The temperature of deep seawater is cold enough to cool the organ meaningfully during a long dive. All confirmed facts. The problem is that no one has directly measured the temperature of the spermaceti organ during a live dive. Attaching a temperature probe to the inside of a diving sperm whale's head has not been achieved. The theory remains unproven. Some researchers argue the energy savings if the buoyancy system works as described would be enormous. Estimates suggest the whale could save a significant portion of the muscular energy a dive would otherwise require, energy that could then be redirected toward hunting, longer dive duration, or simply surviving the next day. Other researchers point out that the spermaceti organ's primary confirmed function is acoustic. The buoyancy control could be a secondary benefit rather than the primary purpose. The organ might have evolved for sound production and buoyancy control, developed as an adaptation to its presence. Both things can be true simultaneously. The ocean's most extreme predator may carry a single organ that handles three separate critical functions at once. The depth that organ takes the whale to is the next number that matters, and when researchers finally recorded the deepest confirmed sperm whale dive ever measured, the number they got back was difficult to believe. The sensor was attached to the whale with a suction cup, a small data recorder designed to detach after a set period and float to the surface for collection, the kind of equipment researchers deploy when they cannot follow an animal where it is going. The whale dove. The recorder tracked depth, time, and movement continuously. When the device surfaced and the data downloaded, the number on the depth record was 7,388 feet. Confirmed. That is the deepest recorded dive from any sperm whale carrying a data logger. 7,000 feet. To put that in physical terms, the Empire State Building stands 1,454 feet tall. Stack 5 of them on top of each other, and you are still over 1,000 feet short of where this whale went. Pile them on the ocean floor, and the whale passed over the top of all 5 on its way down to the bottom. At that depth, sunlight does not exist. Zero. The sun's rays, which penetrate the upper ocean to a few hundred feet in clear water, stop somewhere around 3,000 feet under even the most favorable conditions. Below that, the ocean is permanently absolutely dark. Not dim, dark. The kind of dark where your open eyes and your closed eyes give you the same information. The temperature at 7,000 feet hovers just above freezing. The pressure, as covered earlier, crushes anything not specifically built to handle it. And the whale was down there for close to an hour on a single breath, hunting. What lives at that depth is a population of animals that human eyes rarely see and nets rarely reach. Giant squid, already mentioned, are the headline. But the deep ocean also holds enormous populations of other cephalopods, fish species adapted to total darkness, and bioluminescent creatures that produce their own cold light in the absence of sunlight. The whale can see none of this visually. The eyes are largely irrelevant at that depth. Everything the whale perceives, every piece of spatial information it collects, every prey animal it identifies, happens through sound. The click system described earlier is operating at full power in the darkest, coldest, most pressurized environment on Earth. And the whale is succeeding in that environment every time. The stomach full of fresh squid beaks is the proof. Researchers attach depth recorders to as many whales as possible because each dive profile tells them something new. Some whales dive shallower, hunting different prey. Some individuals consistently hit extreme depths. The deepest dives appear to belong to large adult males, who are both physically large enough to carry more oxygen storage and socially motivated to access hunting grounds that smaller females may not reach. The deepest parts of the ocean, the stretches of water below 5,000 feet, are among the least explored places on Earth. Humans have sent cameras and submersibles to some of these zones, but the coverage is tiny compared to the total volume of deep ocean that exists. The sperm whale has explored all of it for 23 million years. Whatever is alive down there, the whale already knows about it. The whale has been eating it, fighting it, and carrying its remains back to the surface in a stomach full of beaks, long before the first human scientist ever thought to look. And some of what the whale brings up from those depths does not stay inside. Some of it gets transformed, slowly, in the dark of the fourth stomach, into something that defies easy explanation. Deep inside the whale's digestive system, something slow and strange is happening. Most squid beaks get vomited out before they cause any trouble. The whale's body identifies the sharp, hard objects early and expels them through the mouth before they travel far enough to damage the soft tissue of the intestinal walls. This is a confirmed biological reflex, observed in stranded whales and confirmed through analysis of whale vomit recovered at sea. But some beaks slip past. They make it through the first three stomachs and enter the fourth chamber. And there, the whale's body responds to the intrusion in a way that produces one of the rarest and most valuable substances on Earth. The intestinal lining recognizes the sharp edges of the beak as a threat. It begins coating the beak with a waxy, fatty secretion. Layer by layer, the same basic biological logic a pearl uses when an oyster coats a grain of sand. The whale wraps the irritant to protect itself. Over months, possibly years, more beaks accumulate in the same region. Each one gets coated. The individual coated beaks fuse together into a solid mass. That mass grows as new material adheres to its surface. The whole structure hardens slowly into a dense, dark, foul-smelling rock that can weigh anywhere from a few pounds to over 100 pounds in a single whale. This is ambergris, confirmed to form exactly this way from squid beaks in the intestinal tract of sperm whales. Fresh ambergris is dark, almost black, and smells powerfully of animal waste. Anyone who has found a piece on a beach and picked it up reports the same first impression. It smells like the inside of a very old, very unclean barn. But ambergris changes. Exposed to salt water and sunlight over years of floating in the open ocean, the outer layers oxidize and lighten. The interior structure shifts chemically. The foul odor fades and is replaced by something completely different. A deep, warm, earthy, almost sweet scent that perfumers have prized for centuries. The transformation is real and confirmed. The same substance that smells like sewage when it exits the whale becomes one of the most sought-after fragrance ingredients in the world after years of ocean exposure. Ancient traders in the Arabian Peninsula, finding chunks of it washed ashore, called it ambar, meaning amber, and traded it across continents before anyone knew what animal produced it. For most of recorded human history, the origin of ambergris was a genuine mystery. People found it floating in the ocean or washed up on beaches. It had no obvious source. Theories ranged from solidified sea foam to the eggs of seabirds to mineral deposits from the seafloor. The connection to sperm whales came only after whalers began cutting open whale intestines in the 17 and 1800s and finding the dark masses inside. Even then, exactly how the whale gets rid of it remained unclear, and the two leading theories about expulsion are very different in their implications for the whale's survival. One of those theories involves a process that is completely natural and harmless. The other involves something that researchers describe as potentially fatal, and the disagreement between the two camps has never been fully resolved. The chemistry behind the transformation of ambergris is one of the more surprising stories in marine biology, because it involves a molecule that should not be valuable at all. The primary active compound in aged ambergris is called ambrane. It is an odorless alcohol. By itself, it smells like nothing. It has no fragrance. If you isolated it in a lab and held it under your nose, you would detect nothing remarkable. But ambrane does something unusual when it comes into contact with fragrant molecules from other sources. It binds to them. It slows their evaporation. A perfume that would normally fade within an hour or two on the skin lingers for many hours longer when ambrane is present. Perfumers call substances that do this fixatives. Ambrane is the most effective natural fixative ever discovered. This property makes ambergris the reason your great-grandmother's perfume still smelled the same at the end of the day as it did in the morning. The expensive perfumes of the 18th and 19th centuries used ambergris as a foundation. Without it, the top notes and heart notes of a fragrance evaporated too quickly to justify the price. The transformation from foul to fragrant happens through oxidation. Salt water, sunlight, and atmospheric oxygen slowly break down the dark outer layers of fresh ambergris. As those outer compounds degrade, they produce a series of smaller molecules with their own scents, earthy, woody, warm, and slightly marine, that combine with the ambrane base to create the characteristic ambergris smell. The longer a piece floats, the more transformed it becomes. The most valuable pieces are pale grey or nearly white on the outside, indicating years of ocean exposure. The interior of those aged pieces still carries traces of the original dark material, including the squid beaks at the core. Crack open a pale aged chunk of ambergris, and the squid beaks are still there, preserved inside, proof of where the whole structure began. The value follows from the rarity and the fixative property. Ambergris has traded for prices that match or exceed the price of gold per pound throughout history and into the present day. A single large mass, well-aged, found floating in the South Pacific or washed up on a remote beach, represents a find worth tens of thousands of dollars to the right buyer. Several countries have complicated legal relationships with ambergris. In the United States, trading in it falls under endangered species protections for sperm whales, making the sale illegal regardless of how the ambergris was found. In other countries, trade is permitted because the substance is a natural excretion with no harm to the living animal. That legal question circles back to a biological one. The ambergris has to leave the whale somehow, and the two possible exit routes lead to very different conclusions about what this substance means for the animal carrying it. The harmless version involves normal passage through the digestive system, the mass moving through and exiting without incident. The dangerous version involves something rupturing under the weight and pressure of a growing mass. Which one actually happens most of the time is something scientists have debated for decades without a final answer. The modern perfume industry solved the ambergris supply problem decades ago by synthesizing ambrane in a laboratory. Confirmed. Most high-end perfumes today use a synthetic compound called ambroxide, which replicates the fixative and scent properties of natural ambrane without requiring any whale product at all. But the market for natural ambergris never disappeared. It simply shifted. Collectors, historians of fragrance, and certain artisan perfumers still seek natural ambergris. Some argue the synthetic version does not fully replicate the complex mix of secondary compounds produced by years of ocean oxidation. Others value it purely as a historical object, a connection to the era before synthetic chemistry changed the industry. A small number of traditional perfume houses in France and the Middle East still incorporate small amounts of natural ambergris into their most expensive formulations. The price fluctuates by age, color, and provenance, meaning where it was found and how it was handled. A piece found floating in the open ocean, pale, firm, and well-aged, commands more than a piece found fresh near a whale carcass. The former has completed the oxidation process. The latter still smells like animal waste and requires years of additional processing before it becomes useful. The people who find ambergris are almost always surprised. Beachcombers in New Zealand, fishermen in the Maldives, coastal walkers in the Canary Islands. They pick up what looks like a pale waxy rock, sometimes confused for a piece of drift pumice or a lump of solidified foam. The smell is the giveaway. Rub the surface, and the scent that rises is distinctive enough that experienced ambergris traders identify it immediately. Some finders cash in quickly through specialized brokers. Others hold pieces for years, knowing that additional aging increases value. A piece the size of a cantaloupe, well aged, has sold at auction for prices exceeding $50,000. The global production of natural ambergris is tiny, confirmed. Only about 5% of sperm whale carcasses examined by researchers contain ambergris. The reasons for that low percentage are not fully understood. One possibility is that most whales successfully pass or expel the material before it accumulates to a detectable size. Another is that the conditions necessary for mass formation, specific beak accumulation in the fourth stomach combined with the right intestinal secretion response, are individually rare. A third possibility is that large masses form in many whales, but are expelled at sea and drift away before washing ashore. The 5% figure comes from examined carcasses. The ocean keeps its own inventory, and floating ambergris that never reaches a beach goes uncounted. What the perfume industry learned from ambergris eventually led to a broader study of animal-derived fixatives. Scientists examining ambrane's molecular structure contributed to research on olfactory receptors in the human nose, work that later informed drug development for smell-related neurological conditions. A substance formed in the intestine of a deep-diving whale around indigestible squid beaks contributed to human medicine, the ocean connecting to the laboratory in the most unlikely way possible. But the question of how the ambergris leaves the whale alive, or whether it always does, leads to the most disturbing theory in this entire story. This is a theory, not confirmed, but the evidence behind it is serious enough that marine biologists include it in standard discussions of sperm whale pathology. The concern is mass size. Most ambergris recovered from whale intestines is relatively small, ranging from a few pounds to perhaps 20 or 30 pounds. Masses of this size, while abnormal, could theoretically be passed through the digestive system if the intestinal walls expand sufficiently, or could be broken apart by intestinal movement over time. But the largest documented masses are a different matter entirely. Pieces of ambergris weighing over 100 pounds have been recovered from sperm whale intestines. Some accounts, less rigorously documented, describe masses approaching twice that weight. A 100-pound solid mass inside the intestinal tract of even a 60-ton animal is a substantial obstruction. At some threshold of size, the mass stops being something the body can manage. The intestine cannot expand enough to pass it. The muscular contractions of the gut cannot break it apart because the surface has hardened. The mass simply sits there, growing larger as new material adheres to it, pressing against the intestinal walls with increasing force. If the mass grows large enough, researchers believe it could eventually cause a rupture of the intestinal wall. A perforation in the intestine releases its contents into the body cavity. In any mammal, this produces a systemic infection that progresses rapidly and is almost always fatal without surgical intervention. A sperm whale has no access to surgical intervention. The theory suggests that some whales carrying large ambergris masses die as a direct result of those masses. The ambergris, having grown past the point of safe expulsion, kills the animal from the inside. The counter-argument from skeptics is that ambergris expulsion through normal digestion is possible and probably common. Whales vomit frequently and deliberately, especially when processing indigestible material. A growing mass might be expelled this way before it reaches a fatal size. The relatively small percentage of carcasses containing ambergris could indicate that most whales successfully manage and expel the material before it becomes dangerous. The honest position is that no one has directly observed either outcome in a living whale. The intestinal conditions of a living, actively diving sperm whale are impossible to monitor with current technology. The evidence from carcasses shows some whales dying with large masses intact. Whether those masses caused the death, or simply accumulated after death from an unrelated cause, is difficult to determine. What is confirmed? Ambergris masses found in dead whales occasionally show signs of intestinal trauma around the point of contact, tissue damage consistent with chronic pressure, in some cases, perforation. An animal capable of surviving pressures that crush submarines, capable of fighting giant squid in total darkness, capable of mourning its dead and teaching its young, may also be vulnerable to a slow, internal process that builds over years and ends in rupture. The ocean's most extreme predator, killed by something the size of a suitcase growing inside it. What makes this stranger is how rarely it appears to happen, given how many whales carry the early stages of ambergris formation. The body has defenses we have not fully mapped yet. 5%. That is the confirmed figure from documented sperm whale necropsies. Walk through 100 dead sperm whales and roughly 5 of them will have ambergris somewhere in their digestive system. The other 95 show no sign of it. The question that number raises is not just about ambergris. It reveals how little scientists understand about the whale's internal biology, even after 2 centuries of study. The most straightforward explanation is that the other 95 whales successfully expelled whatever beaks accumulated before a mass could form. The whale vomits early and often. Most beaks never make it past the first stomach. The few that do get cleared before the coating process reaches a critical stage. Only in a small number of individuals does the accumulation outpace the expulsion. But this explanation has a gap. Researchers do not know why expulsion fails in some whales and succeeds in others. The anatomy is the same across individuals. The diet is similar within a population, yet some whales form ambergris and some do not, with no clear anatomical or behavioral predictor identified so far. One hypothesis involves individual variation in the strength of the vomiting reflex. Some whales may simply be more effective at clearing their first stomach early, while others allow more material to pass before triggering the reflex. This kind of individual variation exists in almost every biological system, but nobody has measured it directly in sperm whales. A second hypothesis involves diet specificity. Not all squid have beaks of the same hardness or shape. Some deep-sea squid species produce beaks that are particularly angular and resistant to early digestion. Whales hunting in regions where these species are more common might be more likely to develop ambergris because the beaks more often evade early expulsion. This hypothesis predicts that ambergris prevalence should vary by geographic region based on local prey species. Some limited data supports this. Ambergris finds cluster in certain ocean regions more than others. Whether that reflects prey distribution, ocean current patterns that concentrate floating ambergris near certain coastlines, or actual differences in whale diet is not determined. A third hypothesis, the most speculative but not dismissed, involves gut microbiome variation. The population of microorganisms living in a whale's digestive system varies between individuals and affects how digestion proceeds. A different microbial community might produce different amounts of the waxy secretion that coats the beaks, affecting whether a mass forms quickly, slowly, or not at all. No one has mapped the sperm whale gut microbiome in enough detail to test this hypothesis directly. The 5% figure, sitting there calmly in the research literature, represents the edge of what scientists know. Beyond it is a question about individual biology that the whale has not answered yet. And that individual mystery connects to a broader one. How much individual variation exists across sperm whales? Because what researchers found when they started reading the outside of the whale's body suggested that each animal is far more distinct than anyone expected. A marine biologist with enough photographs and enough patience can identify individual sperm whales by sight, not by radio tags, not by genetic sampling. By looking at the skin, every whale carries a combination of markings that accumulates over a lifetime and never repeats exactly in another individual. The circular squid sucker scars, the toothrake marks from other whales, the irregular patches of discoloration from old injuries, the patterns of barnacle attachment along the belly and flanks. Each element adds a layer to a record that grows more detailed with every passing year. Barnacle colonies on cetaceans are underappreciated as biological records. Barnacles attach to slow-moving or stationary surfaces in specific ocean temperatures. A whale that spends winter months in warm equatorial water and summer months in colder high-latitude feeding grounds carries barnacles from both regions at different points in its life. As barnacles die off and new ones attach, the colonies shift in composition. A researcher familiar with the barnacle species of different ocean regions can read a whale's recent migration history directly from its skin. The circular scars from giant squid suction cups provide a size record of past hunts. Larger circles mean larger squid. A whale carrying very large circular scars dove to extreme depth repeatedly and engaged squid large enough to fight back meaningfully. The size of the healed scars tells researchers how old those encounters were, because scar tissue changes over time in predictable ways. Tooth rake marks from other sperm whales tell social history. Fresh rake marks suggest recent conflict with another whale. Old, fully healed rake marks from early in life suggest the whale survived juvenile social disputes. The position and angle of the marks sometimes reveals whether the attacker was larger or smaller than the whale being studied. Collectively, these surface records function as a biography. Researchers who follow specific individuals over years can match new photographs to old ones and track how that individual's life history is written onto its body in real time. This kind of long-term photo identification of individual whales has revealed something scientifically important. Sperm whales show strong individual personality variation. Some individuals are consistently more aggressive in social interactions. Some are consistently more exploratory, traveling farther from the core pod range. Some are more involved in calf care. These differences persist over years of observation. Individual personality, long-term consistent behavioral differences between members of the same species, was considered a human or primate characteristic for most of the history of animal research. Finding it clearly expressed in ocean-dwelling mammals the size of a school bus forced a recalibration of how researchers think about animal cognition generally. The skin also records something else, something that researchers initially dismissed as behavioral quirk before accumulating enough observations to take it seriously. The whales sometimes stop moving entirely. They hang in the water, vertical and motionless, in groups, silent, unresponsive to boats approaching nearby. What that behavior is, and what it might reveal about sperm whale consciousness, is unlike anything else in the ocean. A research vessel in the Pacific moved quietly through a patch of calm water and came upon a group of sperm whales standing vertically in the water, heads pointed toward the surface, flukes hanging below, completely motionless. The vessel drifted close. The whales did not react. They stayed in position, floating like enormous buoys, arranged in a loose cluster about half the length of a football field across. The crew watched. The whales kept not moving. For several minutes, nothing changed. Then one whale stirred, rose slightly, breathed, and sank back into its vertical position. Scientists who reviewed the footage and later studied similar encounters concluded these whales were sleeping. Confirmed behavior now documented across multiple ocean regions and multiple research groups. Sperm whales sleep vertically, in pods, at the surface, with their heads pointed up and their bodies hanging below them, suspended by the positive buoyancy of their blubber and the slight negative buoyancy of their denser lower bodies, balancing into a neutral floating position. The behavior occurs in short cycles. A typical sleep episode lasts around 10 to 15 minutes. The whale breathes periodically during this time, rising slightly to exhale and inhale, then settling back into position. Researchers studying the brain activity of smaller cetaceans in similar states found that one hemisphere of the brain reduces activity while the other remains partially alert, a form of sleep that allows the animal to keep breathing voluntarily without fully waking. This is called euhemispheric sleep, common across many cetacean species. One side of the brain rests, the other watches. The animal never becomes fully unconscious. The vertical orientation appears specific to sperm whales among large whales. Other whale species sleep horizontally at or near the surface. The vertical position in sperm whales may relate to the weight distribution of the enormous square head. With the heavy head pointing upward, the whale's body hangs in a natural equilibrium that requires minimal muscular effort to maintain. Sleeping pods typically include multiple individuals arranged in loose formation. Some researchers believe the grouping offers protection from sharks, which are unlikely to approach a cluster of animals this large. Others believe the grouping is simply a reflection of the social bonds within the pod. The whales sleep near their family members the same way they do everything else. The depth at which sleeping occurs varies. Some pods were observed sleeping with their rostrums, the tip of the upper jaw, just above the waterline in light chop. Others appeared to sleep a few feet below the surface, rising only when the breathing interval arrived. The discovery of sleeping behavior in sperm whales added a detail to the picture of this animal that had been absent from research for centuries. It was always assumed the whale was either diving, traveling, socializing, or hunting. Sleeping was not prominently discussed because nobody had directly observed it clearly enough to document. The sleeping whale is vulnerable, temporarily less alert, and surrounded by family members who apparently do the same thing in coordinated cycles, so that the pod is never entirely asleep at once. A social coordination of vulnerability, built on trust between animals that have known each other for decades. The clicks that bind those animals together across an entire ocean tell an even longer story. Sound travels 4 times faster in water than in air. In the deep ocean, in a temperature layer called the deep sound channel, sound travels even more efficiently, bouncing between thermal layers without dissipating into the seafloor or the surface. A sound produced in this channel can travel thousands of miles with remarkably little energy loss. Sperm whale clicks enter this channel. Their frequency and power allow them to propagate through the deep sound channel to distances that strain comprehension. Research vessels have detected sperm whale clicks more than a mile away using standard hydrophones. In optimal ocean conditions, using more sensitive equipment, the detectable range extends much further. The practical implication is that 2 sperm whales separated by a significant stretch of open ocean can acoustically detect each other. A whale in one part of the Atlantic could potentially receive click signals from another whale well beyond visual range, beyond the range of any biological sense except hearing, and identify the source as another sperm whale through the characteristic sound signature. Whether whales use this capability for deliberate long-distance communication or simply passively encounter each other's signals is a question scientists have not fully answered. What is confirmed is that sperm whale acoustic signals travel far enough that the ocean is never acoustically empty of them. In any active sperm whale habitat, some level of click traffic is present almost continuously. The implications for social coordination are significant. A pod separated during a foraging dive could potentially maintain acoustic contact across distances that would make visual or physical contact impossible. A lone male traveling between female pod territories could detect the presence of a pod by its click signature before visual contact. Pods moving through the same region at different times might deposit acoustic information in the water column that trailing individuals can detect hours later, not as intentional communication, but as a byproduct of normal echolocation. The ocean, from the sperm whale's acoustic perspective, is a vast information-rich environment. Every click produces data, every echo returns data, every other whale's click adds data to the ambient soundscape. The whale navigates, hunts, and socializes within a continuous flow of acoustic information that humans could not perceive without technology. Researchers who study underwater acoustics describe monitoring a sperm whale-rich area as listening to a living, moving conversation that never fully stops. Click patterns overlap, interact, and layer on top of each other in ways that are structured enough to suggest meaningful exchange, but complex enough to resist simple decoding. The complexity of that exchange increases dramatically when researchers compare the click patterns of whales from different ocean regions, because those patterns are different, consistently, reliably, regionally different, and the differences are passed down through generations. A pod of sperm whales in the Caribbean clicks differently from a pod in the Pacific. The difference is specific, consistent, and preserved across generations, confirmed through decades of acoustic research and photo identification studies. The researchers who first noticed this were not looking for it. They were cataloging click patterns to try to understand the function of different click types. When they started comparing recordings from different ocean regions, a pattern emerged. The click sequences that pods use for social communication, called codas, varied by family group and by geographic region in ways that could not be explained by random individual variation. A coda is a specific rhythm of clicks. Think of it as a beat pattern: 3 clicks, then 2 quick ones, then 1, or 5 evenly spaced clicks. Each pod has a repertoire of codas that its members produce consistently. When researchers record a pod and catalog its coda repertoire, then record the same pod years later, the repertoire is stable. The same patterns appear. The whales are using the same click vocabulary as they did years before. When researchers record different pods from the same ocean region, those pods share some codas and diverge on others. Pods from different ocean regions share fewer codas overall. The pattern is exactly what you would expect if the codas were cultural, meaning learned and transmitted through social interaction rather than genetically determined. A calf born into a Caribbean pod does not arrive with Caribbean click patterns built in. It learns them. Over months of close social contact with its mother and other pod members, it practices clicking and gradually converges on the patterns used by its group. Researchers have recorded juvenile sperm whales producing coda attempts that are close to but not quite matching the adult versions, the acoustic equivalent of a child learning to pronounce words. This is cultural transmission, confirmed in sperm whales. The same basic mechanism by which human languages are passed from parents to children operates in sperm whale pods, applied to patterns of click rather than patterns of sound in air. The implications go beyond linguistics. Cultural transmission in a species means that behaviors, knowledge, and social conventions can spread through a population faster than genetic change. A useful new coda pattern, or a new hunting strategy, or a new defensive behavior can spread from one individual to an entire pod within a generation, and to neighboring pods within a few generations. This is exactly how human technology and culture spread, ideas moving through a social network faster than genes can move through a breeding population. The evidence for cultural transmission in sperm whales forced a revision of what researchers considered unique to humans and our closest relatives. The capacity for culture, for learned group behavior passed down through generations, appears to exist in an animal that separated from our evolutionary line over 90 million years ago. Two completely independent evolutionary lines, separated by nearly all of animal history, arrived at the same solution. Teach your young, maintain traditions, vary your signals by group. And that cultural transmission extends beyond click patterns. Evidence suggests it reaches into survival behavior that may have developed specifically in response to human hunting. This is a theory, but the evidence behind it is strong enough that several serious marine biologists have published on it. During the peak of the American whaling era in the 1800s, hunting ships reported a change in sperm whale behavior that developed over decades. Early in the industry, whales responded to approaching ships with curiosity or mild avoidance. By the mid-1800s, large male sperm whales were actively charging hunting boats. More significantly, pods of females began using a new formation when threatened. Instead of scattering in panic, which would have been the obvious survival response, and the one that made individual whales easy to separate and kill, pods began grouping into a tight formation with their heads pointed outward and their powerful flukes toward the center. Researchers call this the marguerite formation, named for the flower whose petals it resembles when viewed from above. This arrangement made sense as a defense. A whale's head is its most protected part, the thick skull and spermaceti organ, offering more resistance to a harpoon than the relatively thinner flanks or belly. The calves were protected in the center. The adults presented the hardest targets outward toward the threat. The problem with this tactic was that it also made the whole group stationary and predictable. Whalers quickly learned to exploit it, killing the adults clustered together far more efficiently than they could have caught scattered, fleeing whales. The marguerite formation, however logical as a land predator defense, was catastrophic against human hunters with long-range weapons. Here is the disturbing part. The formation spread. Reports from whaling captains across different ocean regions, with no contact between the whale populations involved, described the same new behavior appearing in whales that had never encountered hunting ships before. The pods behaved as though they knew a ship was a threat before they had been attacked. The most likely explanation researchers offer is that acoustic signals spread the warning. A whale that survived an attack would carry information about the threat. That whale's pod would adjust behavior. When that pod interacted acoustically with other pods over subsequent years, the information propagated through the social network. Behavioral change driven by socially transmitted information. Culture applied to survival. The fact that the defense was strategically flawed does not reduce the significance of the observation. It means the whales attempted a coordinated cultural response to a novel threat, got the strategy wrong because nothing in their evolutionary history had prepared them for humans with explosive harpoons, and paid for the error with their lives. Researchers studying modern sperm whale populations find that whales in areas with historical heavy whaling pressure behave differently around vessels than whales in areas that saw less hunting. Some level of cultural memory of the threat may persist. An animal whose social memory runs for decades, whose culture is transmitted across generations through learned click patterns, may carry echoes of the whaling era in its behavior even now. That behavioral complexity rests on a physical foundation, and one part of that foundation is thermal, the whale's ability to maintain a warm body in a deep ocean that runs just above freezing. Stand in water just above freezing for long enough, and your body loses heat faster than your metabolism can replace it. The process is called hypothermia, and in water that cold, it becomes dangerous within minutes for an unprotected human body. A sperm whale spends significant portions of its life at depths where the water temperature hovers around 35 degrees Fahrenheit. It stays in that water for its internal body temperature remains around 95 degrees Fahrenheit throughout. Confirmed. The whale maintains a temperature difference of 60 degrees between its core and the surrounding water, indefinitely, without external heat input. The primary tool is blubber. The thick layer of fat running under the skin across the whale's body acts as a biological dry suit. Blubber has very low thermal conductivity, meaning it resists the transfer of heat from the warm interior to the cold exterior. The thicker the blubber layer, the slower the heat loss. In large adult male sperm whales, the blubber layer reaches over a foot in thickness across the body. It is not uniform. Areas where blood vessels approach the skin surface, such as the flukes and the trailing edge of the dorsal fin, have thinner blubber, and those areas are used to regulate temperature in the opposite direction. When the whale is too warm, increased blood flow to the flukes transfers excess heat to the water. The flipper and fluke surfaces act as radiators. Inside the flippers and flukes, the blood vessels are arranged in a configuration called a countercurrent heat exchanger. Warm blood from the body's core flows out toward the fluke surface through arteries. Cold blood returning from the cool surface flows back toward the core through veins that wrap around those arteries. The warm outgoing blood heats the cold returning blood before the cold blood can reach the heart and drop core temperature. The heat stays in the system rather than being lost to the water. This vascular arrangement is a confirmed anatomical feature, found throughout marine mammals and studied extensively in dolphins and seals as well as whales. The whale's metabolism also generates heat continuously. Digesting enormous quantities of squid is an energy-intensive process that produces heat as a byproduct. The four-stomach system running at capacity generates meaningful thermal output. The whale is essentially burning fuel continuously, and the heat of that combustion stays trapped inside the blubber insulation. At extreme depths, maintaining body temperature becomes even more critical because the whale's enzyme systems, which drive all its biochemistry, are calibrated to function at around 95 degrees. Drop that temperature significantly, and the enzymes slow down. The whale's ability to process oxygen, contract muscles, and maintain neural activity would all degrade. The body temperature must stay up even in the coldest water. The circulatory system that manages all of this is one of the more extraordinary biological structures in any large animal, and it carries beyond thermal management another adaptation for extreme diving that made researchers reconsider fundamental assumptions about mammalian physiology. Pull a piece of sperm whale muscle out of a carcass and hold it in open air. Within minutes, the tissue turns dark, almost black. The darkness comes from myoglobin, the oxygen-storing protein packed into the whale's muscle cells, at concentrations roughly 10 times higher than in human muscle tissue. Confirmed, myoglobin in human muscle is present in modest amounts. It gives raw meat its red color and stores a small reserve of oxygen in the tissue for short bursts of intense activity. In a sperm whale, the myoglobin concentration is so high it turns the muscle a deep burgundy to black, and the storage capacity it provides is enormous. Before a dive, a sperm whale's muscles are saturated with myoglobin-bound oxygen. When the whale descends and the lungs collapse, cutting off the normal gas exchange that would deliver fresh oxygen through the bloodstream, the muscles draw on that stored supply directly. The whale runs on the oxygen packed into its own tissue, rather than the oxygen in its lungs. The sperm whale is not holding one breath of lung air and stretching it across 90 minutes. It is carrying oxygen distributed throughout its entire muscular system in a stored form that delivers it steadily over the duration of the dive, with far greater efficiency than lung air alone. The blood also differs fundamentally. Sperm whale blood carries hemoglobin, the same oxygen-carrying protein found in all mammal blood. But the hemoglobin molecule is structurally different. It binds to oxygen at lower partial pressures than human hemoglobin does, meaning it picks up oxygen efficiently even when available oxygen concentration is low. At the end of a deep dive, as available oxygen drops to levels that would cause human muscle to cramp and fail, the whale's hemoglobin keeps delivering. The circulatory volume is also adapted. Marine mammals have a proportionally larger blood volume than land animals of similar body mass. A sperm whale carries more blood per pound of body weight than a similarly sized land mammal would, and that extra blood volume provides extra oxygen storage capacity in the hemoglobin itself. The combination of high myoglobin muscle, high volume blood, and high efficiency hemoglobin creates a system that functions like 3 separate oxygen tanks stacked in parallel. The lungs provide the initial supply during the descent. The blood delivers oxygen from hemoglobin through the early and middle phases of the dive. The muscle myoglobin sustains activity in the final phase, when blood oxygen is nearly depleted. All 3 tanks drain in sequence. The whale surfaces when the 3rd tank approaches empty. Researchers studying the oxygen economy of deep diving whales calculated that the 3-system approach allows dive durations several times longer than lung capacity alone would support. The 90-minute confirmed dives fall within the range this system makes possible, with some margin remaining for unusually long hunting attempts. This biology took tens of millions of years to refine, and when the whale finally surfaces after a long dive, it enters a world of light and air where, for a time, it leaves something behind. Something that lasts long after the whale dives again and feeds an entire ecosystem on the seafloor below. A 60-ton sperm whale dies somewhere in the open ocean. Its body sinks, slowly at first, then faster as internal gases are reabsorbed and the tissues lose their buoyancy. Over hours, the carcass descends through the water column, passing through every depth zone the living whale once dove through. Eventually, it reaches the seafloor. What follows is one of the most productive ecological events in the deep ocean. Researchers call it a whale fall, confirmed phenomenon studied directly by placing whale carcasses on the seafloor and sending cameras and submersibles to observe the progression over years. The first phase begins within hours. Sharks, hagfish, and large scavengers detect the chemical plume drifting up from the carcass and converge. They strip the soft tissue rapidly, sometimes removing most of the blubber and muscle within a matter of months. At this scale, the carcass represents more food than the surrounding seafloor would normally receive in years from the slow rain of organic material drifting down from the surface. The second phase begins as the soft tissue diminishes. Smaller organisms move in, crustaceans, polychaete worms, fish that specialize in processing bone. They work through the remaining connective tissue and cartilage. The skeleton becomes the center of activity. The third phase is the longest and most surprising. The whale's bones contain enormous reserves of lipid, the same fat type as the blubber, but stored inside the bone structure itself. Specialized bacteria colonize the bone surface and begin breaking down those lipids. The bacteria release hydrogen sulfide as a byproduct, a gas toxic to most ocean life, but a chemical energy source for a specific community of creatures adapted to use it. This creates a chemosynthetic ecosystem centered on the whale skeleton, tube worms, mussels, snails. Species that normally live only near hydrothermal vents, where hydrogen sulfide bubbles up from volcanic activity, colonize the whale bones and establish a thriving community. Some of these species are found almost exclusively on whale falls and vent sites, suggesting that whale falls may have historically served as stepping stones. Islands of chemical energy scattered across the deep seafloor that allowed vent-adapted species to colonize new vent locations across ocean basins. A single large whale fall can sustain this chemosynthetic community for up to 100 years, confirmed through modeled estimates based on bone lipid content in large whales and observed decay rates in documented whale falls. One whale, 100 years of productivity on the seafloor, a century-long gift to an ecosystem that otherwise survives on scraps. The number of sperm whales that have died naturally in the deep ocean, over 23 million years, each one creating a century of seafloor productivity, adds up to an ecological contribution that shaped the deep ocean ecosystem we study today. The whale fall communities we find are the living descendants of ecosystems built on ancient whale bones. And some of the material inside those ancient whales, specifically the ambergris, survives all of this. Ambergris does not fossilize the way bone does, bone replaces its organic content with minerals over time, turning tissue into stone while preserving the shape. Ambergris, being primarily a waxy organic substance, does not undergo that replacement. And yet researchers have found ancient ambergris in seafloor sediment cores, in coastal deposits, in prehistoric beach material. Chemical analysis of these ancient samples confirms they are ambergris, carrying the signature compounds including degraded ambrane, the distinctive chemical fingerprint of the substance. Some confirmed finds date back over 1 million years, confirmed through radiometric dating methods applied to the sediment layers containing the samples. This single data point lands harder than it initially seems. Modern humans, as a species, have existed for around 300,000 years. The earliest evidence of human ocean navigation dates to perhaps 60,000 years ago. The first confirmed human use of ambergris in fragrance and medicine, based on written records, goes back a few thousand years at most. Sperm whales were producing ambergris in the ocean for hundreds of thousands of years before any human being existed. The substance was forming, accumulating in intestines, being released somehow into the ocean, and floating on currents, washing up on ancient beaches where no person was there to find it. It weathered and transformed for centuries, then washed away or sank and was buried in sediment. The ancient finds also confirm that the sperm whale's internal biology has been operating essentially unchanged for at least 1 million years. The forestomach system, the squid beak accumulation, the intestinal secretion that coats the beaks, all of it was already in place before our species arrived. 1 million years of ambergris production means 1 million years of failed squid beak expulsion in some individuals. 1 million years of the same biological vulnerability operating in one of the ocean's most otherwise resilient animals. The sperm whale survived every major climate shift, every ocean temperature change, every extinction event in the past million years. And through all of it, a small percentage kept forming these masses. The ancient samples also tell researchers something about historical sperm whale populations. Ambergris frequency in sediment layers can serve as a rough proxy for how many whales were present in a given region during a given geological period. Areas with high ancient ambergris concentrations suggest dense historical whale populations. Areas with none suggest the whales were absent or rare. This kind of indirect population reconstruction is imprecise, but in the absence of other records, any signal from the past is useful. Researchers studying human impact on whale populations use these ancient baselines to understand what the ocean looked like before industrial whaling reduced sperm whale numbers by over 60% in 2 centuries. Before the harpoons, the ocean was much louder, the click traffic was denser, the ambergris was more common, the whale falls were more frequent, and the mystery at the center of this animal's head, the battering ram theory about the spermaceti organ, may have been on display more often in the conflicts between the larger populations. The spermaceti organ weighs close to 2,000 pounds in a large adult male. It sits in the front of the skull, protected by the thickest connective tissue in the animal's body, wrapped in a muscular sheath and padded internally by its oil-filled compartments. The frontal surface of the whale, the flat face that meets the water, is reinforced by these internal structures in a way that no known acoustic or buoyancy function requires. Something about the structure of the male sperm whale's head suggests it is built to absorb impacts from the front. The layout of the protective tissue, the orientation of the internal compartments, and the specific reinforcement of the skull directly behind the organ all point toward a head designed to take a hit and keep functioning. Male sperm whales engage in direct physical combat. Confirmed. Scarring patterns from teeth show combat involving jaw locks and biting. But some marine biologists argue that the most significant weapon is the head itself. The evidence begins with the Essex. In 1820, a sperm whale estimated at around 85 feet long rammed the wooden whaling ship Essex twice in the North Pacific, eventually sinking it. the crew abandoned ship in the middle of the ocean. Most died before rescue. The story became one of the most documented maritime disasters of the century, and the direct inspiration for Herman Melville's novel about whaling. The key detail: the whale rammed the ship at full speed, head-on, twice, deliberately, from behavioral accounts. The second ram came after the whale had turned and accelerated from a distance. A second, less famous case occurred in 1851, when another whale rammed and sank the ship Am Alexander off the coast of South America. These were intentional attacks with the head used as a battering ram. The structure of the spermaceti organ, if it functions as both a sound chamber and an impact absorber, would allow the whale to deliver this kind of force, without damaging its own brain on the rebound. Male-on-male competition provides the strongest evolutionary pressure for this adaptation. Two large male sperm whales competing for breeding rights in deep water would benefit from a head that both generates navigational sound and wins direct physical confrontations. An organ that does both is more efficient than two separate structures. Some researchers have modeled the impact force a large male sperm whale could generate by ramming at full speed. The numbers they produce are high enough to account for the documented ship damage. The whale's mass and swimming speed combine to produce a kinetic energy at the moment of impact that would affect a wooden hull seriously. The battering ram function remains an unconfirmed theory. No researcher has directly observed two sperm whales ramming each other head-on underwater at depth. The evidence is indirect: anatomy, historical accounts, and mathematical modeling. But the anatomy is real. The head is built differently from what sound production alone would require. Something about the male sperm whale's head is built for force. And that force, combined with everything else inside this animal, points toward a creature that has made serious scientists deeply uncomfortable when they step back and consider the full picture. Most animals are easier to study when you maintain a certain distance. You observe behavior, measure physiology, catalogue the data, and publish. The animal remains an object of study, a subject, not a person. Sperm whales make that distance difficult to maintain. The evidence accumulated across these chapters builds toward a portrait that researchers approach carefully: an animal with the largest brain on Earth, spindle neurons associated with empathy and social awareness in humans, great apes, and elephants. Grief responses to dead family members, documented across multiple ocean regions by independent research groups. Cooperative childcare built on long-term social memory. Cultural transmission of learned behavior across generations. Regional dialects in a click language that juveniles learn through social exposure. Individual personality variation that persists across decades of observation. Each of these characteristics, taken individually, appears in at least some non-human species, but the combination of all of them in a single species, scaled to a brain of this size, operating in a social structure this complex, is something scientists do not have comfortable language to describe. The cautious position, which most researchers adopt publicly, is that sperm whales demonstrate high cognitive complexity and sophisticated social organization, but their inner experience remains unknown. Consciousness, emotion, subjective suffering are concepts that require more evidence before being formally applied to a species this different from us in body and habitat. The honest position, which some researchers express more carefully in interviews and less formal settings, is that the biological markers of consciousness, social awareness, and emotional experience in this animal are comparable to those in species we routinely describe as sentient. What makes scientists uneasy is the math of what happened to these animals during the whaling era. Sperm whale populations were reduced by more than 60% between the early 1800s and the mid-20th century. Confirmed. Industrial whaling targeted them preferentially because of the spermaceti oil and the potential for ambergris. Tens of thousands of individuals were killed. An animal with a social memory that runs for decades, with grief responses to the deaths of family members, with cultural transmission of knowledge across generations, experience that loss differently from a fish or a reptile. The pods that lost members to whaling ships lost not just individuals, but knowledge, hunting strategies, navigation routes, decades of accumulated experience that could not be replaced. The whale fall data adds another dimension. Each whale that died created a century of seafloor ecosystem productivity. Each whale killed at the surface and processed by a whaling ship produced nothing for the ocean below. The ecological impact of removing tens of thousands of these animals extended down through the water column to the seafloor, affecting communities that had depended on whale falls for geological timescales. The sperm whale cliques that travel across ocean basins are still out there. The pods still exist. The cultural transmission still happens. The pods still grieve. The ambergris still forms in a small percentage of individuals. The spermaceti organ still does things we have not completely explained. 23 million years of evolution produced an animal we are still trying to understand. The ocean that shaped it is deeper than any human technology has fully explored. And somewhere in the dark, right now, a sperm whale is descending past 7,000 feet, clicking in the absolute blackness, mapping a world we have never seen with a sound we can barely measure. It has been doing that since long before we existed. It will carry that mystery and those clicks and those scars long into whatever future the ocean allows.